Welcome to Talks at Google. Today it is a great privilege to be able to introduce Dr. Josef Aschbacher of the European Space Agency, where he directs their program on Earth observation. He's going to speak to us about the big picture from space, from pixels to knowledge. He has led from the very beginning, starting in 1998, the Copernicus program, which is a set of multiple satellite missions that have become the most, I would say, audacious, ambitious, comprehensive set of Earth observation missions ever created, going out with planned launches to 2030, systematically monitoring the entire global set of land, ocean, and atmosphere. And the goal is to derive benefit for society, humanitarian applications, climate, environment, crisis response, and I hope he will speak to us about those things. It involves a huge amount of data. I think they're coordinating delivery of data from upwards of 30 satellites, delivering in excess of 10 petabytes of data each year. We have a cooperation going on now where that data is coming off those satellites and going into the Google Earth Engine platform. By the way, I should introduce myself. I'm Rebecca Moore. I lead the Google Earth Engine projects here at Google. And it's beautiful data that they're producing. Dr. Aschbacher is Austrian. He has more than 35 years of professional experience in Earth observation with a technical background in the natural sciences. And really the essence of his leadership of Copernicus is to shape a future of our planet that will benefit all of us. So please join me in welcoming Dr. Aschbacher.
Okay, so good afternoon. My name is Josef Aschbacher, and thank you very much for Rebecca to introduce me. I'm from the European Space Agency. The European Space Agency is well known all over the world. You probably know NASA, but ESA is the equivalent in Europe, the European Space Agency, doing a lot of activities in the various domains of space. I'm very glad to be here today. Thank you for inviting me, because I really would like to present to you some of the data which we are producing and how these data are being used for everyday's life and how they can really help make our planet a better place. Let me start with one slide which is really showing space, the final frontier. All of you know Spaceship Enterprise. You have all been very fanatically watching it, including myself, and this is really symbolizing that we are at the edge of what can be done and at the edge of what we want to achieve as mankind, but also to explore new domains, not only in outer space, but also in terms of knowledge, in terms of technology, which we are doing as part of our daily work. So what you see here is an image of our planet Earth taken by Rosetta, and Rosetta may be known to you as the satellite which was flying to a faraway comet, which was releasing a sounder called Philae, which was landing on the comet and actually taking measurements. The satellite was taking measurements around the comet and the lander of the comet itself. 500 million kilometers away from our Earth, this satellite was working. However, this image was taken much closer. In fact, the satellite had to fly around the Earth to make these slingshot movements to get to outer space. In this case, 630,000 kilometers, where he took an image, or where the satellite took an image back of our planet Earth, just to show that we are having a very unique vantage point from space in order to look at our planet. But in the European Space Agency, we are also working on other elements, not only outer space and exploring new planets, but also in different domains. We are actually one of the few space agencies worldwide, next to NASA and a very few others, who are covering all the domains, from rockets to navigation systems, to telecommunication, human space flight, and Earth observation, which is the domain I'm heading at the European Space Agency. What is ESA? ESA is composed of 22 member states, countries in Europe that are members and are funding our programs and making decisions on how the money is being spent in the European Space Agency. We also have cooperating states, plus Canada, who are having agreements with us on a long-term basis in order to work on some of these space projects. And the way we usually function or organize our funding is that we are proposing to our member states a proposal which may be attractive to them or not, because it is a voluntary contribution they give to our programs. So it is not a subscription by GNP or other means. We are making a proposal to our member states, and if they like the activity we are doing, they put money into the pot and they participate in the program. And this is a very unique way of how we are doing it, meaning that we have to compete for money, for ideas, in order to really fund our programs which we are doing. We also create inspiration for future explorers, and this is of course the nature of space activities, that it really inspires you and creates your imagination and shows what can be possible. In this case, we are having regularly open days in our facility in Frascati, which is close to Rome, and we are inviting young kids. We show them movies, the astronauts are coming, and as you see, they can get very excited in seeing what can be done. But what I'm doing in particular in my directorate is building satellites and methodologies how to monitor our planet. And there we share a great vision together with Google Earth Engine, who is also looking at the planet, using its capacities, the computing power, to really make good use of the information in order to better understand how the planet is being, what happens on the planet, how it can be better managed, and really derive information for decision makers, but for the general public to make awareness of what the state of our planet is. So what you see here in this graph is the activities of the Directorate of Earth Observation on one chart. These are the lines of satellites which we are operating and developing. At the moment we have 28 satellites that are being under development in our order book, which is actually the largest number ever which we have. We are operating currently 12 satellites, and all of these are rather substantial satellites where a lot of R&D is being invested in order to provide these measurements. You see the three circles here. On the left-hand side, the green circle or the green orbit, which underlines the science missions. So really satellites which are addressing questions of science. And we are developing cutting-edge technology in order to address these questions of science, to answer some very important points which are being raised by the scientific community. Let's take an example, climate change. Scientists have asked us to monitor closely what is the extent of ice coverage, not only the extent of ice coverage, but the volume of ice on the polar regions, and what is their change over time. And we have developed a satellite which is doing exactly that, to monitor regularly ice coverage on a daily basis. The second orbit is the Copernicus orbit, which is which symbolizes those satellites which we call sentinels that are monitoring the planet through the Copernicus program. The Copernicus program is a newer program within the agency, but a very substantive one, because we are doing this with the European Union, who has declared formally Copernicus as one of the two flagship programs in Europe, and together the European Union with the European Commission and the European Space Agency, we are developing a suite of satellites which are monitoring the planet from various angles with various instruments, and I will explain that a bit more in detail in a minute. And then the right-hand side, we have the meteorology missions, where we are building, together with EUMETSAT, which is the equivalent of NOAA in Europe, satellites for weather monitoring, weather observations, both in geostationary orbit and in polar orbits, in order to really see the various aspects of weather and climate parameters. Talking of space and observing the Earth, this is a very good example of the very first image. It's a TIROS satellite, which is a US satellite, which did monitor the Earth in 1960. On the 1st of April, the satellite was taking this first television picture from space. You see the New York Times article, which is referring to it as really a new era in meteorology, which has started with this launch of this satellite. A few years later, now, we are also having satellites observing the Earth for climate and weather purposes. Here are some examples that are measuring and observing constantly the state of cloud coverage, but also other weather parameters through both Meteosat, which is the geostationary satellite, and METOP, which are the polar orbiting satellites, which are going around the Earth, updating the weather services with this type of information. What you see here is a very good example of how satellites work in daily life. In this case, you see Superstorm Sandy, well known in the United States. It was actually a storm that caused quite a few tens of casualties. First in the Caribbean, where you see at the bottom the start of Superstorm Sandy. The storm then went northwards, and at some point of time, meteorological services expected that the storm would turn towards Europe, to the east, and therefore not cause a danger for the Washington, New York area. However, as you see, the actual course of the storm, which is on the right-hand side, showed that the Superstorm Sandy went into the northeastern parts of the American continent and really caused, again, damage, but also casualties at this point of time. Of interest is the image in the middle, which shows these various lines in different colors, which are the forecasts of the path of the storm a few days in advance. In this case, 9.5 days in advance. And you see that there was a wide variety of where the storm will end up. Very few actually indicated that it turns again towards the west, towards the continent, and therefore would cause some damage. And this, of course, was predicted quite well in terms of prediction accuracy. Satellites were used and could predict 6.5 days in advance that the storm actually would turn left rather than right, and therefore some measures were taken in order to improve that. I should probably also say that in global weather forecast, so if you look outside and you hear that the weather tomorrow is sunny or is stormy, satellites today are the major data source for forecast accuracy. If you take all the measurements put together, what we call in situ, which is measurements on the ground, in the atmosphere with radiosondes, by boats, by airplanes, those measurements, which we call in situ measurements, are about 1/3 of the forecast accuracy. The other 2/3 comes from satellites of various nature. And I think this is underlining and highlighting how important satellites have become for our daily life. Another example where satellites are really useful is climate monitoring and monitoring the state of our environment. What you see here is the Paris conference, which was adopting the Paris Agreement, which was a milestone in climate monitoring, but expressed by the political community who have been committing to preserve the planet. And this was a very important moment, and we have committed ourselves as the European Space Agency to use our satellites in support of climate monitoring. Some of these satellites are shown here, the Sentinel satellites. The Copernicus Sentinel satellites are grouped in 5 or in 6 different families. They are using different instruments on board, from radar to optical imagery to larger scale, wider scale measurements of oceans on the land surfaces to atmospheric tracehouse gases. So you see here on the left-hand side Sentinel-1, which is a sensor that provides 10-meter resolution in the radar domain. Sentinel-2, very much used because it has an instrument on board with 13 channels, spectral channels, that can measure the Earth state on a regular basis, like a camera in the visible domain of the electromagnetic spectrum, but also in the near-infrared and shortwave infrared, which gives information on the state of vegetation, for example, but also many other parameters. Sentinel-3 has 3 instruments on board, again for large-scale monitoring of oceans and land masses, various parameters. I will show a few examples in a minute. And Sentinels-4 and 5, atmospheric trace gases that are, of course, at the source of global warming and define the changing climate. So what we do with these satellites is really measuring the Earth system. Different parameters that are all interconnected measure various elements of our planet. Here we see the example of chlorophyll, sea level height, sea surface temperature, nitrous oxide, carbon dioxide, soil moisture, but there are also many other parameters which we are measuring on a regular basis with these satellites. What I'm showing here is actually a complicated graph, and I'm not going to explain all these lines, but there are two messages I would like you to take with you on looking at this graph here. The first message is that the different colors are showing different families of sentinels, meaning different observation technologies, which are really providing measurements of all the parameters of the globe, which are the atmosphere, the oceans, polar regions, which are a system together, and the various sensors which we have put on the sentinels are observing various parts of this system. The second message is long continuous lines, in this case up to 2027, but I could have this graph showing up to 2040, and you would still see that these measurements are taking place over long periods of time, and this is one of the most important features of the Copernicus program, that we are committing ourselves to have satellites that provide these measurements basically forever, meaning that after one generation is coming to the end of its life, a next generation will be flown in space, of course with improved sensors and instruments, and this will be followed by another generation. So really a continuous measurement series of observations, which of course is crucial for anyone to really trust in this data, take them up and use them in the long term. Sentinel-1, one of these sentinels which is measuring various parameters, shown here in an artistic impression. It has a radar instrument as the main instrument. You see here also the solar panels, but the radar instrument is working in C-band and taking images of the Earth day and night, independent of weather conditions, because radar goes through the atmosphere, even if it's clouded, even if it is rainy, even at night, and you can get data of this area. I'm showing now a few examples of what can be measured with these radar images, which are a bit unusual compared to optical images, which you are probably more used to. This is a radar image showing, or different radar images showing the changes of crops, of rice crops in the Vietnam area. And what you see here in the different colors is different states of the planting cycle, which allow you to retrieve a yield, including also some other information. You see here written on the slide that this was a case where we had an El Nino effect. That means some changes in our global system. And we got a loss of the rice yield of about 16% between 2 years, 2015-2016, based due to the effects of El Nino, which caused financial damage, but also people who have been suffering from this El Nino effect by not having the food security required. Another example of what this radar data can do, and this is quite unique, is measuring deformations of the surface itself. You see here an image of Mexico City. You see the red areas, which are areas that have actually sunk in, that have been reduced in terms of surface height due to water which was extracted from underground, drinking water, water for other purposes. And you see here that in 1 month, up to 2.5 centimeters, 1 inch, was actually the change of height. This was done over 3 months. So in 3 months, you had 3 inches of change, or 7.5 centimeters of change in the surface level in the city of Mexico. Almost not believable, but it really happened that buildings and all the structure above was sinking in quite significantly as an effect of this. But it is also surprising that you can measure this from space. Our satellites fly in 800 kilometers altitude, and you can measure accuracies of changes in the structures in the order of millimeters, which is quite astonishing, using a technology called interferometry. And the same technology has been used recently. You see here an example of California, highway number 1, before and after, on the left side before, and on the right side after the landslide which was destroying the highway but also the surrounding area. This happened on May 24th, 2017. And the analysis of the satellite image shows in the red areas that this is the area which was actually sinking in, and you can measure how many centimeters or how many inches these changes have been made. You see here very clearly that in the extreme cases there have been 2 meters of changes in height due to this landslide. But ESA is not only producing Sentinel satellites, but also other satellites which are more geared for scientific use and which are addressing some very key questions of science. What you see here are those what we call Earth explorers that have been launched so far. You see Goche, which is on the left-hand side, SMOS, Cryosat, and Swarm, and I will show some of the examples of the use of this data right now. Goche, which is measuring the geoid of the Earth, is actually having on board a very high precision gradiometer, which is measuring gravity changes or the gravity field of the Earth. You see here the Earth rotating. You might assume the Earth is a round ball. It has a round shape. It does not. It actually looks like a potato if you consider the gravitational field of the planet. And this satellite has actually provided the most accurate gravity measurements ever flown in space. It has deorbited in the meanwhile. It was launched in 2009, and it had a controlled re-entry from the start in 2013, where it measured actually while it was descending, again with high accuracy, these parameters. You also see that this satellite is quite unusual compared to others you may have seen. It looks almost like an airplane. It has wings because it was flying at a much lower altitude compared to others, which was required to make these measurements. Another example is SMOS. SMOS stands for soil moisture and ocean salinity, which is a satellite that is measuring these two parameters, soil moisture over the land surfaces and ocean salinity over ocean surfaces. What you see here are the sea surface salinity values over a period of time. You see the months on the right-hand bottom of this animation. And you see very clearly there are some areas which are more salty and others are less salty. The blue means it is more fresh water, so lower salinity, and the red means higher salinity. Areas which have a very high rainfall, for example, in the tropical area, getting from the water from the clouds are less salty as compared to other areas which are, for example, further up north. Another example of these measurements are measurements by our ice satellite, which is measuring extent but also volume of the ice coverage. You see here the ice volume and mass balance measurements as they are taken by Cryosat satellite, here in the case of Greenland. And you see the cumulative loss of volume of Greenland over a couple of years, which are regularly updated with this satellite. And I should also say that for many years, scientists have actually been arguing, if not fighting, whether there's an increase or a decrease of the mass balance of ice in Greenland. And this was a question which for actually quite a few years was disputed until NASA and ESA have put together their science teams and all the satellite observations which they have through their satellites, but also other means on ground and otherwise, and have compared their data sets and have clearly found out that there is a net mass balance loss, meaning there's a melting which takes place. However, in some of the areas, there is actually also an increase of mass, especially in the central parts of Greenland. For example, seen here in this diagram, which is from a different satellite measurement series from Sentinel-1, but it also shows very clearly by different measurements taken over time where the mass flows, the ice flows actually take place. You see in the middle the bluish areas, which are indicating that there's a slight increase of mass, but of course towards the edges the snow and the ice are melting and flowing towards the coastline. Another mission which is actually quite a challenge for us is the LiDAR mission called Aeolus, which is using a huge LiDAR instrument on board. You see it in this big cone on the satellite, where a LiDAR beam comes out in the ultraviolet and will measure, when it is launched in about half a year's time, will measure wind speed and wind direction in a three-dimensional field in cloud-free atmosphere. Because the LiDAR, the laser beam is actually reflected on the molecules and the particles in the atmosphere. An element is coming back to the satellite, and those elements coming back through the velocity of the satellite allows you to retrieve it in 3 dimensions. Actually, this is a technology which is not existing at all today. We had some technical hurdles to overcome because it is a completely new, unique technology which we are developing here as part of our R&D activities. At some point in time, our engineers got stuck and couldn't figure out some of the issues that were stopping some of their work. We did call NASA for help. NASA said, no, we are not working on this. This is too challenging, but if you figure it out, please tell us how you solve the problem, because it is something we would like to do as well. So we are, actually, I'm knocking on wood, we are looking forward to these measurements. They will be really unique, and I think something that our user community, in this case meteorologists, weather forecasting services, really need to have. So global challenges on a changing planet. This is really something that concerns everyone, not only our space agencies, but really every single citizen on this globe. We are working a lot in this domain. You see here the SDGs, the Sustainable Development Goals, as they have been approved by the UN system, which are indicating a number of goals, targets, and indicators which are important in order to preserve our planet. You see some blue ticks on these boxes. These are the ones where space can help providing critical measurements, and we are doing this. We're setting up a program that will address many of these indicators with the means of satellites in order to really understand the state of the planet, but also help improving its state. One example is urbanization. You see here Shanghai, an image taken in 1975, in 1990, in 2000, and in 2010, and you see how rapidly this city was evolving. What you see in red color here is the built-up area, so basically really the area which was changing over the last few days very rapidly, and this is typically one of the parameters that can be measured from space. Another measurement we are taking, very important, very critical, is sea level rise. We all know from newspapers, from TV, that global change is causing, among other things, an increase in temperature, but also an increase of sea level height, which has been recorded here since 1700, over several hundred years already, based on ground measurements and records on the surface. Then you see this window here, which is the window when satellites started taking very precise measurements of sea level changes. And then on the right-hand side, you see the future projections. Future projections meaning, depending on how much global change we accept, how much temperature increases we have, in which direction these curves will go. And you see, first of all, the curves all point upwards, which is scary. But also the variation is quite high, meaning that it depends a lot on how mankind in total will behave over the next years in order to decide whether we are on the upper curve, on the middle curve, or on the lower curve. And of course, we hope we are on the lower curve, because that would be the lower impact. But what you also see on the right-hand side is that this is a curve of sea level rise, which is going up very clearly, measured from space in this case, with very independent means. You see here over the last 20 years that the sea level, on average, was rising about 3 millimeters per year. 3 millimeters may not sound a lot, but if it's 10 years, 20 years, or 100 years, it is a very important amount of sea level rise, of course leading to some areas that will be flooded, small islands in the Pacific disappearing, some cities on the coastlines being underwater and not anymore livable, and it is quite difficult to imagine that this will actually happen, but it is measured and it will be happening, no doubt. The same shown here, again sea level rise on the left-hand side, sea surface temperature on the right-hand side. These are measurements which have been taken by satellites. First of all, you see that the sea level is not only changing on average across the globe, but has very strong local variations. These, of course, depend on weather, on various ocean circulation elements. You see, for example, very clearly the Gulf Stream from Florida towards Europe, which has this red-blue currents, which is having a very large change of sea level along its way. Also, surface temperature, sea surface temperature on the right-hand side, also changing accordingly depending on weather, depending on ocean circulation, and a number of parameters. Other parameters we are measuring regularly with our satellites are the extent of ice coverage, in this case the Arctic. It is actually very interesting to see how over the years, and you see the scale at the bottom, the maximum extent of ice cover is really changing. It is known, and this is not surprising, that different winters or different years have different extents. Some are more cold, some are less cold than the previous one. But there's one clear trend, and you see it here, that the further you go forward in the scale towards 2000, 2010, the less ice coverage you have in the polar regions. And this leads already, and even more in the future, to some areas being ice-free, which used to be covered by ice, which has, of course, huge impacts for many, many elements, for climate parameters, but also ship routing, for example. You can, for example, here go from Europe towards Japan using the northeastern passage, meaning going through the Arctic area instead of all the way around in Africa and all the way to Japan, which of course is much longer and therefore also much more expensive. But it does also threaten the environment and the ecosystem in these areas, because ships are suddenly crossing this area which did not cross the area before. So all this is really showing what satellites can measure and how they can be used. So what do we do in the European Space Agency, but this is happening everywhere, especially also here in Google, that the space data are being combined with all other assets, ICT assets, other information which are becoming available in order to produce information which is very relevant, but also integrated into all levels of society, and therefore really being used for everything on a daily scale. You see here a bit the scale from space 1.0 to 2.0, 3.0 towards 4.0, which you would also know as new space, where you combine these various elements. What are these elements? What you see here, there are new actors that suddenly came to life and were introduced in the space domain, which did not exist before and have not been there before. One of them, very prominently, Google. Google has been very active also in the satellite domain with Terabella, but these have been sold. But with the Google Earth Engine project or program, really producing an information source which will be of global value for everyone, not only decision makers, but everyone, to provide up-to-date satellite-based information for various purposes. But also other players are coming on the surface. We have Planet, not far from here. We have Spire, not far from here, who are building constellations of hundreds of satellites, which we didn't have until a very few years ago. So that the landscape is really changing very drastically in our domain. This affects us all, public organizations like the European Space Agency, but also private organizations which are making good use of this data. And we are determined to really interact very closely for the benefit of the community. So what are we doing as ESA to respond to these global challenges? We have organized actually a seminar in May 2017 in Frascati at the European Space Agency's ESRIN facility near Rome in Italy. And we've invited some of the leading experts in these new space domains, in those domains where the biggest changes, the fastest changes are happening. We have invited two types of people. One group of people are CEOs or leaders in building new constellations, satellite constellations with tens or hundreds of satellites that are coming up. Another group of people who are working with this data and converting them into information using ICT technology. And you see here the bottom row on the right-hand side, Noel Gorlik from Google Earth Engine, who was one of our key speakers. And him, together with his colleagues, were really showing us how fast these developments are going, what is happening in the world. And I have to say that our community has been really woken up by this presentation. So it was actually something that was a small revolution, at least in Europe, to see how fast these developments go and what has to be done in order to remain relevant and to interact with these communities. The event itself was a live broadcast. We had several tens of thousands of viewers, not only the people sitting in the room, but people watching the movies either live or afterwards, and this created quite some interest. Which also showed to us that we have to move and we have to act in order to stay on top of it and to connect with these communities. What we have done, and this is something which is more specific to ESA, but goes way beyond ESA, have created something called the Phi Lab, Phi for the Greek letter Phi, or in American Anglo-Saxon pronunciation we call it Phi Lab, which is an open space concept where you invite people with different expertise, with different assets, bring them together, work on a project, and then bring this expertise or this knowledge back home to their company, to the institution, in order to work on specific problems. I'm inviting Google, but also many other partners, to come with us, spend 6 months, 1 year, or longer, or shorter, and identify a project. Let me take an example. Today, at least in ESA, we are not yet using artificial intelligence for the analysis of satellite images. But we know from other domains that this is an area where huge progress is made. Google is one of the key players in this domain, but there are quite a few very active, very prominent companies working on this. We know that this technology will be very useful for satellite images. Take cloud cover as one example, automatic detection of cloud cover, but also some features related to agriculture, to forestry, to archaeology, to many parameters which you can see in satellite images. The huge amounts of data we are producing require that artificial intelligence would really help in identifying some of these key features. Of course, it always needs the human intelligence, but because the volumes are so huge, it is also required that we need to apply these means. And this is one example where we could say Google with artificial intelligence, ESA with its knowledge of satellite data interpretation and the access to its data firsthand, because we produce the Sentinel data, could work extremely well together and develop algorithms, methods in order to help developing methods to save our planet or to preserve our planet with the information which we provide. And I would hope that this is something that would not only put a mirror to us, what happens in technology development, but also to society, and show them how fast our planet is changing and what has to be done in order to preserve it, which then leads to decisions that are actually leading to a preservation of our planet. Another example which we are initiating now in terms of addressing some of these issues is to, together with the European Commission, define a new satellite, we call it Sentinel-7, which would measure carbon dioxide, but at a scale where you can really see where it comes from in order to have a more accurate understanding of the sources, and therefore also what can be done to reduce or minimize these sources. What you see here is an animation, a simulation which does not yet exist from space, but it shows how such a satellite constellation could work, that you really can see where are the sources of emissions, how do they transport through the atmosphere, how do they mix up with other gases, and what is the whole dynamics of greenhouse gases and how it works. And this, of course, would be extremely relevant information in the context of the Paris Agreement, in the context of global climate change, but actually in the context of really seeing what happens to our planet. And this is something we would like to pursue, to build up such a constellation, probably of 3 satellites at the beginning, in order to provide these measurements at a routine basis. What you see on the right-hand side is actually the measurements of carbon dioxide as they have been made through various sources, in this case from 2002 to 2016, but the curve is has a very clear trend, a very clear direction. It goes upwards, and we need to contain this development. But also, information from space has to be useful for everyone. It has to go into devices which you use every day, mobile phones, tablets, for example, air quality, sunshine duration, smart farming. Various users should use this data in an integrated fashion, not only using information from space, but combining it with other data, with other measurements, and with models in order to really make it a daily asset, a daily commodity, which people use just as your weather forecast or any other information you get on your mobile phones. We are also supporting app camps, hackathons, these type of things. But I'm also showing this, this image here because Googleplex is here seen from Sentinel-2, which you know it better where it is, but it's somewhere in the center of this image. But Google actually spreads out over a much larger area. And this is one example of the satellite data showing this area here. Foresight, where do we want to go? What do we think is a way where the use of satellites will end up? And this is one example which shows what we call a control room for Spaceship Earth. It brings us back to the beginning of the talk where we said that the Earth is a spaceship and we are working at the frontier of exploration. And I think we should establish a system that monitors the key parameters of our planet in order to understand, first of all, what happens, but also to provide this awareness and information to decision makers in order to do everything in order to preserve our planet. And with this, I want to thank you very much for your attention, and I'm more than happy to answer any questions you may have.
Are there any missions that you've not planned yet that you think would have a big impact, or that you wish in your own heart that you could do?
Yes, there are a number of missions. There are many more missions than we have money. But there is, in fact, what we do is we are testing new methods or new technologies, and we are developing new mission concepts. We are having an internal catalog of some 50 of those missions, which really go across the whole range. And some of them have shown carbon dioxide as one of the next challenges which we want to develop. But there are also other missions that are using, for example, hyperspectral channels, as we call them, which is not only 10 channels of an imager, but maybe hundreds or even several hundreds of these channels to have a very accurate distinction of the electromagnetic spectrum and understand extremely well what happens on each place of the wavelength in order to have a better distinction between agricultural crops used for mining, different rock types, and so on, to get a much better knowledge of the measurement on the surface. But there are many applications or many ideas which we have in order to measure various parameters. I think one trend is clear. People would like more and more up-to-date information of the state of the whole planet and all the parameters of the planet. And this is really an information they want frequently. We used to have satellite images once every couple of weeks or maybe even months, depending on what the data were. And I think the population really wants to see a continuous evolution of what happens almost every day or even shorter than this within the day of certain parameters. And that's certainly a trend which is also very strong.
So you talked a little bit about, or you alluded to companies like Planet and Spire that are launching constellations of small spacecraft. But the roadmap for the Copernicus that you talked about is still primarily oriented around launching large satellites of the traditional sort. How do you see miniaturization of space technology and privatization of space technology changing how organizations like ESA do your own business in the decades ahead?
Well, this is an extremely good question, and that actually it's the main reason why we organized this event I was mentioning before, to realize, or make people realize what happens, how fast these changes go, and to question, if I may, whether the current approach is the one that goes for the next 10, 20, or 30 years, or we have to rethink, sometimes radically rethink, our approach. And this is really at the core of the debate we are having. How do missions that are built by public institutions like ESA relate to these constellations, which are of very different nature in terms of satellites and information they provide? My personal opinion is it will always need high quality, highly calibrated reference missions, which the private industry may not want to engage because simply they are very expensive and very complex to build, and therefore the business case may not be as evident as you might imagine. However, there are gaps to be filled, and really gaps, meaning in the sense of temporal acquisitions. For example, our sentinels are covering the globe every 5 days. We learn from Planet that they need information every day or even within the day, so very frequent observations. Therefore, they are closing a time gap, but they are also improving the resolution. Our satellites are having 10-meter resolution with a very wide swath. Planet satellites are going down at the moment, the doves 3 to 4 meters, but the newer generations SkySat below 1 meter. And this is something which is a complementary information. And personally, I think the combination of these publicly funded reference missions and privately funded missions, constellations, is extremely useful. And I think there's a lot of work to be done in order to integrate those data sets and use them together.
So you showed that slide with the whole constellation of sensors, current and into the future. And I think the concern is that with that volume of data, we'll be drowning in data, thirsty for knowledge. Where do you see the role of space agencies, NASA, ESA, JAXA, in bridging that gap? And do you think that's a proper role for these agencies, or is that more of an academic and or private sector activity?
Okay, there are several aspects to this question, which is actually a very relevant one. Today, we are producing extremely high volumes of data. Actually, the Sentinel program is the 3rd largest producer of data in the world. To express it in more common terms, the amount of data we produce every day with our Sentinels is more than all the photos, all the videos uploaded on Facebook every day. So it's huge amounts of data which we are managing and which we are producing. And we need the help of large ICT companies, Google and others, to really make good use of this data. The data itself is, of course, fantastic because they provide the baseline of the observations, but the real value is converting this data into information. And this is where companies come in, commercial companies in particular, who convert this data into information. And this, for me, will be one of the biggest challenges in the years to come to manage these massive amounts of data. It's not enough just to screen them. You need automatic methods, artificial intelligence, but also other methods in order to really make good use of this data. I'm coming from Austria, and maybe I take a small anecdote of Mozart, well-known musician. And he, at some point, was looking at a piece of a composition of one of his competitor or fellow musicians. And he was looking at it, and he said, there are too many notes. This is too many data, too many notes. They don't make sense. They don't sound good. The trick is, or the challenge is, to pick out the right notes, put them in the right place, and make a nice melody. And that's what he did. And I think we have the same problem. We have a lot of data, not saying too many, but a lot of data, and picking out the right pieces of information and putting them in the right context is the challenge of the next years to come. And there we need to work a lot all together, not only ESA. This is a work which space agencies have to do with private industry and with a lot of other partners.
Hi, my question is on a lot of the technology that's used in a satellite requires really deep knowledge, like the SAR they talk about and hyperspectra, and a lot of this requires many years of specialization. But to make use of the data more meaningfully, do you think we need to bridge the technical gap between the experts and others of us in like the ICTs who are more comfortable with maybe like machine learning, artificial intelligence, but might not have the knowledge to exploit the data generated by the satellites?
A very good point. I think there are different types of answers to your question, because there is some data which can easily be interpreted using, I would say, computing power. If you take an imaging sensor and you compare changes before and after, you can easily see a difference between one day and another, simply because a forest area has been deforested, or a building has been built, or something happened, and you can easily detect it, I would say, almost automatically with ICT technology. And this is maybe the simpler case, but there will be a lot which you can do with relatively simple means in using this data. There is other use of this data which requires very high knowledge expertise. I showed some of the examples before, what we call interferometry. that you can detect actually changes in height at the surface. And there you need really the expertise of a remote sensing or Earth observation expert in order to interpret, to calculate, interpret these data. So it needs a combination of both. Like always, if you really want to maximize the use of these data, you need the expertise on one side, but also the means on the other side, and the means in this case is really ICT.
So I noticed the focus on where all the effort is of monitoring the planet has been largely Europe and North America focused, both the space agencies and the private sector. How much do we need other parts of the world to get engaged, and how much does it matter, given that these satellites are actually global?
As you say, satellites are global by nature, so a satellite doesn't only stay over America or over Europe or over a certain country. They circulate around the Earth and therefore really take images of the whole globe. So by nature, it's a global issue which requires all the partners. I think I take one good example which really underlines that you need everyone or the major players to work together. Take CO2, carbon dioxide measurements, which is not an isolated problem, because if you pollute here and don't pollute there, it's no good, because if the pollution goes from here to there, and therefore the effect of the clean country or clean area is not working, because the pollution comes from somewhere else through the wind, which transports it. So you need the various countries or regions to work together. Even if Europe says we want to be pioneers in measuring CO2, for example, to better understand the fluxes in the atmosphere and to see what are the impacts on climate change, it's not enough. Europe is a small piece on the whole globe, and it requires everyone. And that's why we really want to engage with all the major space nations, with JAXA, with Japanese, with the Chinese, with America, our European partners, to create a global system, because only a global system is really something that is sustainable and makes sense.
I think we were all very inspired by the vision you articulated and the commitment coming out of Europe, the European Space Agency, to monitoring the planet, going out decades for the benefit of all of us at a time when it is critically important. So my question for you is more personal. When you're turning these pixels to knowledge, some of that knowledge is rather dark that is discovered: melting polar ice, desertification, loss of air quality, all sorts of issues. How do you can you maintain optimism for yourself and your 500+ person team in the face of all this?
Indeed, it's true that sometimes when you monitor closely the state and the evolution of our planet, the news is no good news, because we see how it degrades, how it is being destroyed, how the pollution affects various elements, how climate change increases, temperature increases, sea level rise increases, and so on. This is no good news. On the other side, our planet is so beautiful. And we once had an exhibition where we put together some of our Sentinel or satellite images, mostly from Sentinels, but not only, and have put them on the wall. The title of this exhibition was Beauty and Fragility of Our Planet. And it is so true. Our planet is so beautiful, especially seen from space, but it's also fragile. And I think this fragility is the one that wants you to protect it, because at the end it is your living space, it is our living space, which we need to protect. So, and to answer your question, yes, there is a lot of dangers or threats which we see every day. However, stepping back, the planet has so much beauty to offer, and I think this is really giving you the optimism you need in order to really enjoy this, looking at these images every day.
Thank you very much.
Thank you.